Okay, good morning. Before we begin, do you have any questions? Okay, so to remind you, last time we were discussing 10.1 and 10.2. Basically, right, that reinforces the idea of random sample, which is basically an IID collection of random variables x1 up to xn. Then we discussed, right, our very first statistic, the sample mean, which is x bar, that is the sum, right, divided by n. And so x bar has the following properties. That is expectation, right, is always, okay. So maybe I forgot to say this, right? The random sample here, right, the population mean would be mu and population variance will be sigma squared. That's part of the assumption, right? That's part of the model. So expectation of x bar will be always the population mean. The variance of x bar will always be sigma squared over n. And these two are universal, meaning they do not depend on any assumption on the population distribution. Okay, it holds for any population distribution. So you can have normal, exponential, uniform. This is always true. Of course, like if it's uniform, then that uniform family is not given, right, in terms of mu and sigma square. It's given in terms of the A and B, right, the min max. So you have to be careful to translate that back to the language of mu and sigma square. Same for example, exponential, right? But as long as you know what the population mean, right, and population variance is, then these two statements for the sample mean always holds. The next one is specific, right, for normal population. If you have a normal population, then the sample mean is also normal with mean mu and variance sigma square over n. Finally, we have the asymptotic result that says x bar is approximately normal with mean mu and variance sigma square over n as n goes to infinity. Okay. So as we go along, uh, I'd like you to pay attention to the difference between C and D. C is what I would call a exact result, meaning it's true for any n, even n equals to 2 or 3, right? True for any n. True for any sample size. Okay. And so it's useful in the sense that in reality, you may not have an opportunity to have a large sample. So if you want to say that your sample mean is a normal distribution, then you better make sure, right, that the population is also normally distributed. But on the hand, of course, the restriction is that you don't always have population coming from normal distribution. So even though it's exact, it's true for any n, it's a bit useless on this assumption. The other side, right, is here the asymptotic result is true for any distribution, but it's an approximation. Okay. So in other words, the price you pay here is that you must have a large enough sample size, and large enough sample size changes from distribution to distribution. It's hard to say when, right, the sample size is large enough. And of course, large enough also is connected with how much error are you willing to tolerate, okay? Because this is never going to be exactly this case. In other words, the distribution of X bar looks approximately like normal. What kind of error are you willing to tolerate also is connected to how large the sample size you were willing, okay, you must have. Anyway, right? These two results come hand in hand, and from the point of view of studying statistics, you want to be able to distinguish, okay, between these two cases. So anyway, right? These four are the fundamentals of sample mean. I want to point out quickly that we'll skip 10.3. This is about another kind of sample. Okay, it's sampling with replacement. So in other words, you sample from a population, but you do not put your sample back. You keep sampling. So what that does is that you have a non-independent sample. It's interesting, in some situations, but in a lot of practice, or at least a lot of statistics I have seen, uh, is I have not seen people discussing non-independent sample that much. So we won't go into this in details at all. So the discussion today is 10.4. The textbook call it the chi-square distribution. By the way, right, this is the notation for chi-square with n degrees of freedom. The apologize, chapter 8. Why do I say chapter 10? Thank you. Yeah. So the real discussion actually is about the sample variance. Okay. So first of all, right, the context is we're going to have, again, an IID sample with size n. Okay. So for now, let's not make any assumption about the population distribution, but just say it has some mean and some variance. So the sample variance, S square, will be defined as the sum of xi minus x bar square divided by n minus 1. Okay. So here, of course, right, the sum is sum from 1 to n. Okay. The sum is sum from 1 to n. This is a sample variance. So the sample variance is meant to be an estimate for the population mean, for the population variance sigma squared. Okay. So remember, the population parameters are constants, but always assume unknown. Okay. The context is they're constants, meaning they're not random, but they're unknown. All right. So our task is to use the sample, okay, and the sample statistic to be able to deduce information on the unknown population parameters. So the sample variance in particular is meant to give you information on the population variance. So 8.4 basically is a study of the properties of the sample variance as a random variable. So several things, right? First of all, pay attention to the way S square is defined. I think it's very intuitive that, S square basically is the average, right? Is the average distance of the sample away from its mean, away from the sample mean. So S square, right, plays a role similar to the variance of a random variable. it measures the average spread, right? It measures the average spread of the sample around the sample mean. So that's why it makes perfect sense to be an estimate for sigma square, okay? Of course, so that's just the intuition. S square itself is a random variable, right? So what are its properties? So the plan is going to be as followed. First, we will show that expectation of S square will always be sigma square. So in that sense, it's very similar to the statement that the expectation of the sample mean is always the population mean. So here, the expectation of the sample variance is always the population variance. So the sample variance, even though being a random variable, right, every time you do a sample, it's a different value. On average, right, it's on target, meaning on average, it centers around the true value. Okay. This result is universal. In other words, it's true for any population distribution. So you do not need you don't need any assumption. Well, now beyond this, unfortunately, things get more hairy, okay, more complex. The reason is the sample variance structurally is a much more complicated object than the sample mean, okay. The square here, right, plays a role. Also, as I mentioned before, xi minus x bar as a sequence of random variables are not independent, okay. So x1 minus x bar, for example, is generally not independent of x2 minus x bar, for example. Or you can just calculate the covariance between these two guys, and you see that the covariance should not be zero. So in other words, right, that generally not independent. So when you want to investigate the sum of non-independent variables, or for that matter, just even the variance, right, of the sum of non-independent variables, that will be a challenging task. Okay. So remember, one of the particular easy way for us to calculate the variance of x bar is because the xi are independent. So we did not have any covariance term in the calculation of variance x bar. Anyway, so what I'm trying to say here is that beyond the expectation of S squared, any other statement in terms of universal statement that does not require any population distribution assumption will be tough. So beyond this calculation, we will start making assumption about the population distribution. And so the assumption we'll make is that the sample is drawn from a normal distribution. All right, so the population distribution is normal. What we want to show, okay, what we want to accomplish, so this is the ultimate goal, that n minus 1 s square over sigma square will have a chi-square n minus 1 distribution. So this is the sampling distribution of the sample variance. Under, of course, right, the normal assumption. But that's a very popular result that will be quoted over and over again. So this is a very fundamental result that actually this is the result for this section, okay? And we'll be using this again and again in this class. But of course, right, to be able to show this, okay, to show number 2, we need several items. First, right, define what a chi-square distribution is, because I suppose many of you do not have an idea of what a chi-square distribution is. It's not one of the classical ones you learned from 477. B, we want to state a very important properties of chi-square. Namely this: if you have x, which is chi-square with n1 degrees of freedom, y, which is chi-square with n2 degrees of freedom, and they're independent, then if you sum them up, they will have also chi-square distribution, but with degrees of freedom n1 plus n2. So this is like a closure of the chi-square family, okay? But in a little bit different way. So it should remind you like the Poisson closure or the normal closure. Some independent Poisson gives you Poisson, some independent normal give you normal. So some independent chi-squares give you chi-square, okay? But degrees of freedom get added. And then from these two, okay, we will go back and prove this statement using property A and B, properties A and B. So that's the program. So actually what we'll do is we will do 1, 3, and then go back to 2. All right, that's the program. Any question? All right, so let's show 1, okay? So what is S squared again? S squared, right, is sum of xi minus x bar squared divided by n minus 1. So you could say that expectation of S squared is just sum, right, of expectation of xi minus x bar squared divided by n minus 1. Now, because these are identical, all the expectations are equal. So you could say that this is n over n minus 1 expectation of x1 minus x bar. Okay? So this is because they are identically distributed. So all the expectation terms are equal for all i's. Okay? So in other words, the calculation here requires you to just calculate this expectation of the square. And then you just multiply with n over n minus 1. That's a viable path. And I think some students, some people have done that before in this way. We won't take this path, all right? I mean, it's okay. The reason we won't take this path is because there's another way that's slightly easier, but it will require an identity. And this identity will be useful for us to talk about item 2 and 3. So for that reason, okay, we will just introduce the identity and use that identity to prove this statement. And then also the identity will prove a important role for item 2 and 3. So we will use a different approach, okay? Via this identity. So the identity is going to be as follows. The sum xi minus x bar squared will be the sum of xi minus mu squared plus n x bar minus mu squared. Okay. So I think the textbook definitely mentions this identity, and they also ask you to prove it in problem 8.22. Okay, but anyway, oh, sorry, I messed up the, it's like this, mu here and x bar here, okay? So what does this identity do? This identity, what it accomplishes, okay? What it accomplishes is here, this right here is the term that is related to the sample variance. Yes, that's n times. That's right, n being the sample size. Yes, the last term is n times that, yeah. So this term, right, is essentially our sample variance, okay, with the n minus 1 missing. Now, remember, right, I mentioned that the difficulty of understanding the sample variance, part of it has to do with the fact that the X bar and the Xi are included together, right? So that's kind of the thing where we say X1 minus X bar is not independent of X2 minus X bar, etc. So by writing, right, by this identity, you can decompose the sample variance into two pieces. This piece and this piece. X bar by itself is a single random variable. Now, under the normal assumption, it's a normal random variable, so it's easy to understand. These guys, right, Xi being independent, Xi minus mu are also independent because mu is a constant. So this identity, what it accomplishes is kind of split the action of X bar out into two pieces. Okay, each of the individual pieces are easy to understand. So that's the accomplishment of this identity. Also, right, how do you kind of feel this? How do you kind of feel this identity in terms of algebra? In terms of algebra, or in terms of like the structure of how this works, what happens is this, that this measures the average distance, okay, or the sum. Actually, is called, you can think of it as like sum of squares. Yes, we will show that, Christine. We'll show why it's true. I think essentially you're right. Basically, this end right here is basically like that. And because there's no I in it, it becomes n times that. Yeah. So they're just sum of squares, okay? But in terms of average distance, the X bar is the one that minimizes, okay, the average distance away from all the other points on the sample. That's why, right, if you insert any other points on it, the average distance of Xi, the total distance, I guess, of Xi away from mu will be always larger than the total distance of Xi away from X bar. X bar is the smallest one. It's the point that minimizes that average distance, the sum of square distance. And so it says that the sum of square distance of Xi away from mu is the sum of square distance of Xi away from X bar plus, right, the distance of X bar away from mu. That's the meaning of it. And these kind of statements actually show up a lot in courses like analysis of variance, ANOVA, for example, or regression analysis. You see this a lot. Anyway, so you're asked to prove this, okay, in the text, but I'll show you why it's true. So proof. Why it's true, I think, I'm not sure, Christine kind of alluded to the proof. The idea is very simple here. You start with the left-hand side, and you add and subtract X bar. Okay. Now you add and subtract X bar, you just open up, use the, the quadratic, the binomial formula on this. So that becomes Xi minus X bar square plus X bar minus mu square plus twice Xi minus X bar minus mu. Okay. So this obviously is this. This obviously is this. Okay, because this has no I in it. So that shows that in order for this to be true, that means the cross term must be 0. Or as we like to say, this term is orthogonal to this term. Okay. Now, why is that true? Well, actually, it's also very simple. If you look at this, you see that X bar minus mu, again, has no I in it. So it's a constant in terms of the sum. In other words, right, this term only can be factored out like this. Right? But it's a fact of life that sum of Xi is exactly equal to sum of X bar being, right, just sum of Xi. So these guys being equal, this will be 0. And so this term disappears, and we get our identity. Any question on this? Okay. So now this identity will allow us to compute the expectation of S squared. So how so, right? So let's write that identity down again. So our goal, right, is to compute this expectation. So that means we need to compute this expectation, and then we're done. So what is expectation of xi minus mu square? What is expectation of xi minus mu square? What do you mean, Yasmin? First term, you mean this? No, because there's xi in here, right? Oh, I think you make the mistake. This is not this square, like this. You're not summing it up first and then square it. You square them inside before you sum. You understand the difference? Here you square them first. Yeah, no, right? Because this basically is sum of non-zero terms. It cannot be 0 unless all of them are equal for some reason. Yeah. Okay. All right, so what is expectation of this square? So I hope it's clear that it's exactly variance of xi, because xi, remember, right, we're under the assumption, oh, well, here we don't even need to, right? The xi has mean mu and variance sigma square. So this is exactly the definition of variance of xi, right? And so this is exactly sigma square. Okay. What about expectation of x bar minus mu square? Well, I hope you also see that it is variance of x bar, because again, right, x bar has expectation mu, right? So this is right. This is exactly from our work on x bar, right? Okay. So here, that's because of that. So putting these pieces together, you see that what we have is expectation of the sum of xi minus x bar square will be, right, this sum, but that's n terms, right, of sigma square. So that's n sigma square minus this term, which is n of sigma square over n. So that's sigma square. Therefore, it is n minus 1 sigma square. Then, right, s square being the sum of this guy divided by n minus 1, it's obvious that expectation of s square will be sigma square. Here. So are you okay with this? I assume you're okay with this, right? So here, I put this together, right? So I take expectation on both sides. Now, expectation goes inside, right? Expectation goes inside the sum. So because each of these terms has expectation sigma square, I sum them up. There are n terms here. That would be n sigma square. I bring this over as a subtraction. This term has sigma square over n. So therefore, it's n times that. If you want, I can do this. Maybe that helps. Is that okay? Yeah. Any other question? Okay, so we're done with item 1. All right, we're done with item 1 now, meaning to show this. And by the way, right, notice that nowhere here I make any assumption on the normal distribution, right? None of this calculation requires the normal assumption. So therefore, right, this calculation is independent of the normal assumption of the population. I want to make one more remark. And I think this is kind of a side thing, but a lot of students or people in general kind of got perplexed when they first saw the sample variance because they expect that we should divide by n instead of n minus 1, right? Because it's the average. So, you would expect something like this. Okay. But in this class, I mean, I don't know what people would call this in general, but in this class, I will reserve this notation for it, S prime. S prime is the division by n instead of n minus 1. So in terms of estimator, there's no reason why you cannot use S prime square, in other words, division by n, as an estimator for the population variance sigma square. But a critique or someone may say, well, this may not be a very good estimator because its expectation, right, on average, if you use this, well, because it's divided by n, right, you see that an obvious relation is n times s prime square divided by n minus 1 will be s square. So therefore, right, expectation of s prime square will be n minus 1 over n times sigma square. So it will not be on target in general, right? In general, it will be slightly underestimating the sample variance if you were to use division by n. And so that's the critique. Or again, right, for those of you who know the lingual, s square is unbiased for sigma square, while division by n, s prime square is not unbiased for sigma square. We will introduce the unbiased terminology later on. But I just want to kind of point out that this is exactly the reason, the motivation for division by n minus 1. Okay, so that in general, your estimator is on target. But when n is large, right, the difference here is trivial. When n is large, even when n is 30, you see it. 29 over 30 is not that big of a deal. So that's why I say it's not that bad. Nothing wrong with using this. But if you want to be kind of rigorous, or you insist on unbiased estimator, then S squared is what you use. And people always traditionally go with this anyway. Another comment I want to make on this is the idea of degrees of freedom. Okay. And I'm sure this is a term that you hear a lot as well before if you get anywhere close to statistics. So you will hear something, well, without precise meaning, that S squared, right, this guy right here, is associated with n minus 1 degrees of freedom. Okay, so I just want to give you an intuitive idea of what's going on with this statement. So degrees of freedom obviously means, you know, coming from linear algebra, where is freedom of choice of variable. Okay, so why is it that s squared, right, being involved with n terms, only has n minus 1 degrees of freedom? The reason is this. The reason is in calculating s squared, okay, we need to impose a value for x bar. Or if you want to use a statistical term, we need to estimate mu. Okay, so you use 1 degree of freedom. This costs 1 degree of freedom. So in other words, you have n variables, right? There are many ways you can look at it. You have n variables, but if you tie down its average, then you cannot choose all n values freely. You can only have n minus 1 values freely. You can only choose n minus 1 values freely. Okay, let me give you an example. Suppose you have x and y. But suppose you also insist that x plus y over 2 must be 0. Then clearly, right, you cannot choose x and y arbitrarily, because the moment you choose x, y must be minus x. So right here, there's only 1 degree of freedom. So in general, right, in any estimator where you use some of your sample to estimate some statistic to go into that estimator. So here the estimator is for s squared. You use your sample to estimate x bar to go into the estimator of s squared. That costs you 1 degree of freedom. And that's why, right, you have n minus 1 degrees of freedom because of that. All right, that's the meaning. Because later on, when you do regression, or if you have seen the regression, usually you have something like n minus p degrees of freedom, where p is the number of coefficients in your regression. It's because you use, so many sample. You have to estimate that many parameters from your sample, and so you lose that many degrees of freedom by estimating these coefficients. Here you estimate x bar, so you lose 1 degree of freedom. All right. Any question on this? All right. Maybe one last remark on this, because again, this idea of degrees of freedom are quite fascinating. You imagine it like this, all right? Suppose that mu is known. If mu is known, what's going to be a good estimator for sigma square? If you know the true population mean, what should be a good estimator for sigma hat square? It should be xi minus mu square over n. No. You are, pardon the word, but you're confusing between stat and probability, right? Variance of x bar is the probabilistic properties of the sample mean. But when you want to do an estimator, that means you pull together your sample, okay, to give information on, to give a numerical value, to give a guess to the unknown, right? So variance x bar actually, when you think about it, is a very mysterious object, right? Because yes, we calculate variance x bar to be sigma square over n, but if your boss asks you, okay, what is it? then you cannot say it, right? Because obviously you do not know sigma square, right? So this is a probabilistic statement, but in terms of statistics, is not used. Does that make sense? Or you can use it, but you must substitute the guess for sigma square into the statement. All right. So that's one thing that I hope slowly to bring to light to you guys, that when you make statistical statement, you must be super careful not to use unknown parameters in your statement. So here, right, the estimator for sigma hat can be this, because I assume mu is known, which is super, right, unrealistic in real life. But I just want to demonstrate the idea that if mu is known, then you do not need to substitute the guess of x bar into mu. So in this situation, you will have n degrees of freedom because you do not guess anything. Okay. But in the situation where mu is unknown, then you must substitute the guess for mu into this. And so therefore, it's n minus 1 degrees of freedom. Is this okay? All right, very good. Any question? All right, so moving on then, okay, to the agenda of proving, right? Now we assume that the population has normal distribution. Our goal is to show that S squared has chi-square n minus 1 distribution. All right. So like I said, before we even can attempt this, we must know what a chi-square distribution is. So we'll go back to this, right? And we go to item 3, which is chi-square distribution. Okay. And like I said, knowing a distribution completely could mean several things, but one of the things is to know its density. All right. So here we would just introduce the chi-square distribution by its density. All right. So, but this is not the only way. After I do this, I'll tell you a more practical way that people think about it. But I would say that X has chi-square degrees of freedom, chi-square distribution with n degrees of freedom, if, right, the density of X will be X to the n over 2 minus 1, e to the minus x over 2, and divide by 2 to the n over 2 gamma of n over 2 for x positive. Okay. Yeah. So first of all, right, if you are not used to this kind of thing, when you see this density, I think the first reaction is, being, I guess, perplexed or stressed or whatever, right? What's going on here? A bunch of symbols, right? But so unravel this, all right? Do not be worried about it too much. Several things going on here. First of all, this is what we call the integrating constant. So in other words, I think one of your homework question, right, asks you to determine the integrating constant of some unknown density. So for all intent and purposes, what we care about is the structure of the density more than the constant. Okay. So basically, the identifying factor of a chi-square chi-square distribution with n degrees of freedom are these two terms right here. Okay, why so? Because once you write down these two terms, then this guy must be fixed. This guy must be determined. How? Because k, right, is forced. Why? Because you require that the integral of the density must be 1. Is in under the fraction. What is in the fraction? Oh, the whole thing? Yeah. So so what do I want to say here? The fraction includes 1 over this. And then x and the other one are above the fraction. Okay. So gamma. Also, I will tell you what gamma is later. Yeah, it's called gamma. It's the gamma function. So yeah, actually exactly the point I want to say here is that it's not super important for what we're doing right here. You don't even need to understand what it is for what we're going to do next. Because what I want to talk about, or what we will use mostly, is just this right here. Okay, and that actually is a good philosophical point you want to remember when you work with probability. I know a lot of students just carry a bunch of constants in front of densities and just make their calculation that much scarier. The reason is, again, right, a lot of times you just worry about the structure of the density, because the structure of the density is enough to identify what it is. You do not need to worry about what the constant in front is, because it must be something like this. So in other words, right, k must be 1 over the integral of x to the n over 2 minus 1 e to minus x over 2 dx. K must be this. And then again, I know some of you will say, I am confused because this looks like a scary quantity that we don't know what it is. I agree. But the point is that actually you brought in Calculus 1 point of view to a more advanced course. Calculus 1 exactly requires you to calculate this out, and that's a scary task. From our point of view, for the advanced point of view, this is a determined constant. It's a constant. We don't care for what it is, okay? Because when you try to think about it, is writing this more illuminating than writing gamma n over 2? They're just trading symbols with symbols, okay? I know gamma has a fixed meaning established by the literature, and you can like look them up, right, using online code, Python, whatever. But right, philosophically speaking, this and this are no difference in terms of information. So what I'm trying to say is, right, when we study a density, right, do not worry about the constant in front so much for a lot of purposes. Okay, but yes, in case you wonder, the gamma, right, is a gamma function is a generalization of the factorial. So for example, right, if you have an integer, then it will be n minus 1 factorial. But the point is that this allows for non-integer value. So you can calculate like 1/2 factorial. What that means, okay? So the definition is meant to generalize the property of factorial in some way. But again, that doesn't concern us so much. What we want to do is just to work with density in some way, okay? And what do we want to do? Our main goal is to prove the statement that if x is chi-square n1, y is chi-square n2, and they are independent, then the sum will be a chi-square n1 plus n2. Okay. Actually, there's another, that's a softer statement. For those who are into mathematics, this is like an induction statement. I tell you how to sum things up. But I want to tell you the base case. What's the base case? The base case is the case when chi-square with 1 degree of freedom. That's the base case. And actually, if you have 1 degree of freedom, it's a very easy definition. It's going to be the square of a standard normal. So the standard normal, so basically, right, the way we think of chi-square, I mentioned, right, you can define it by density, that's fine. But the practical way people think of chi-square is this, that chi-square 1 is a standard normal square. Any other chi-square, because of property A, right? So A and B implies that chi-square n, okay, chi-square with n degrees of freedom, will be exactly the sum of n independent normal square. And that's how you think of chi-square. Any question on this? So this is the working definition of chi-square that we'll be using. Okay, question on this. You see how we can go from A and B to this, right? So also, all right, that's also the taste of statistics, or the taste of how we work with probability in this class. So I know that I harp a lot on density and things like that, but density is a useful fundamental thing that we fall back on when we start defining the distribution. But we quickly move away from the density once we can establish what we know. In other words, of course, to establish A and B, you need to rely on density or something like that. But once you are done with that, then all you need to do is to keep the working definition, because most of the time you will not touch, all right, the density level, the distribution at the density level. So do remember that. Choosing the right working definition, choosing the right framework to think about will help your work moving along a lot, okay? If anytime you see a chi-square and you try to remember density, that's really not the right framework to think about, at least in statistics, okay, as far as I know. All right, so our goal then, right, is to show A and B. Let me show you B first, okay? Because actually B we have showed in the review on the very first day of class, but let's repeat that question. So suppose that Y is a standard normal square. How do I find the density of Y? I find the density of Y by starting with the CDF of Y. And that would be, right, the probability of Z squared less than or equal to Y, which will be probability of minus square root Y less than Z less than square root Y. Because standard normal is symmetric, that will be twice probability of 0. And because the probability that the standard normal less than 1/2, less than 0 being 1/2, I can write this as this. So now what I need to do, right, to find the density of Y, of big Y, is to differentiate with respect to small y. So the density of Y is differentiating, right, this with respect to small y. But because this is a CDF of the standard normal, then if I differentiate, I get the PDF evaluated at this times the derivative of this by chain rule. So all in all, I have 2 the standard normal density evaluate square root y times 1/2 square root y. Well, let's plug in and see what I get. I get, right, the 2 and 2 cancel. I get y to a minus 1/2, if you will. And then I got e to the standard normal density is e to minus z squared over 2, right? So it's going to be e to minus y over 2. and then I get 1 over square of 2 pi. Is that okay? Now, how do I know that this is chi-square 1? How do I know that this is chi-square 1? Well, let's compare that with the chi-square, right, density that we know. If x is chi-square n, by definition that we just wrote above, its density will be 1 over 2 to the n over 2, gamma of n over 2, x to the minus, sorry, n over 2 minus 1, e to the minus x over 2. Okay. And so I guess here, actually, you also see what I mean by constant doesn't matter. To identify distribution at the density level, you just need to match the structure of the density. Okay. So this match with this. And then clearly, right, this matches with this when n equals to 1. Right? And of course, here n equals to 1 gives you square root of 2. So coincidentally, you discover that gamma 1/2 is equal to square root of pi, right? Square root of pi. So, all right. But you see, actually, I don't care about that so much. The moment I see this, and I know for sure that there are densities, then I know for sure this is a chi-square 1. Okay. Any question? So I establish B. How do I establish A? Well, there's a painful way to establish A, and there's an easy way to establish A. The painful way to establish A is to work at the density level, okay? Because the density of the chi-square, as you see, right, is not super pleasant to work with at the, a more general level of N. So to establish A, what we will want to do, and what you do with sum of independent variables, random variables, the nicest tool you can think of is moment-generating function. Because moment-generating function works very well, right, with sum of independent random variables, as you have seen, right, hopefully from your quiz. So we'll establish that if x is chi-square, we will establish, okay, that if x is chi-square with n degrees of freedom, then its moment-generating function is 1 minus 2t to the minus n over 2, or let me do this, 1 over 1 minus 2t raised to n over 2. Okay, like this. So I'll say this. It's an easy calculation, quote, easy, because if you know what you're doing, then it's easy, right? Because what it does is you must integrate this from 0 to infinity e to a tx times this. And you must show that somehow it's this, okay? It's easy if you look at it the right way. So, in the interest of time, I'm not trying to cheat here. I can show you, but there are many things I want to show you today. So I will leave it as a quiz, okay? So you figure it out. I'll give you a hint. You combine these two exponential terms and do a change of variable. It's very quick, all right? But let's accept this, okay? And I'll ask you to verify that as a homework problem. So accepting this, then the statement A is very easy to show. Why? Because remember, right, x is chi-square n1, y is chi-square n2. They're being independent. So remember, right, one of the beautiful property of independent moment, the moment generating function of independent sum of independent, right, random variables is the product of um, moment generating functions. Okay. So the x being chi-square n1, that would be 1 over 1 minus 2t raised to n1 over 2. Y being chi-square n2 will be 1 over 1 minus 2t raised to n2. But you see, the beautiful thing about this is that they are both, right, they both can combine to become 1 over 1 minus 2t raised to n1 plus n2 over 2. And that's it, right? Because moment generating function being the unique identifier of a random variable of a distribution, you look at this and you say, well, x plus y having this moment generating function, then it must be a chi-square with n1 plus n2 degrees of freedom. And that's it. Any question? All right. One more thing, I believe that I used the notation phi for moment generating function. The textbook used m. You want me to switch back to phi here, or m is fine? You understand what I'm talking about, right? I mean, just in case you're concerned, I don't use the same notation. I think I used phi before for this. Okay. All right, cool. All right, so now we have all the tools we need, all right, to establish what we want. So let's go back to what we want. What we want, right, is to show that n minus 1 s squared over sigma squared has a chi-square with n degrees of freedom, which is a question mark here. All right, so what do I need? So of course, right, what I need is that identity that I talked about before. This identity, you will see why this identity is very useful right now. So remember, the identity is sum of xi minus mu square is sum of xi minus x bar square plus n x bar minus mu square. This quantity right here, right, I hope you realize is exactly n minus 1 s squared. Okay. Therefore, right, what you're saying is take this, which is this, and divide by sigma square. So what happens is we should divide everything by sigma square. So that is sum, right, of xi minus mu over sigma square is n minus 1 s square over sigma square plus n x bar minus mu over sigma. Let me do this, making it even more beautiful. Is that okay? Any question on this? So again, I hope you see why this identity is super useful. So we're after this distribution. This identity allows us to decompose this distribution into two individual distributions. And so if we can figure out these two guys, we know what this is, all right, at least in spirit. So let's see. So let's look at the easy piece. X bar minus mu over sigma over root n. Remember, right, we are under the normal assumption now. In other words, x1 up to xn are IID normal mu sigma square. What distribution does this have? What distribution does this have? Standard normal, exactly, right? And that comes from our work on showing that this is normal mu sigma square over n. All right, you see how all the pieces, right, are tied together. We need some, um, you know, foundational knowledge, right, to move on to the next step. But yes, right, because of this, this is exactly standard normal. Therefore, what distribution does this have? What does this have? Exactly, by what we just said before. Very good. Now, then let's move on to this piece, right? What distribution does xi minus mu over sigma have? Also standard normal, right? By this. By the way, right, whenever I write z in this class without saying much, right, z is understood as a standard normal distribution. So then what distribution does this have? Well, remember, right, the zi are independent. Exactly. So that's exactly the working definition that we were talking about, right? That this exactly will be the sum of NIID standard normal square. So that will have a chi-square distribution with n degrees of freedom. All right. So that seems like, right, the end of the story, that we have a chi-square n here. We have a chi-square 1 here. Then that must imply that this is chi-square n minus 1. Is that correct? So, right, that seems like we got all the pieces of the puzzle here. Well, the answer is no, not really. Because if you really press, right, the question and ask, well, why? What result are you quoting? Then you may say, well, didn't you just say, right, chi-square n1 plus chi-square n2 is chi-square n1 plus n2? And I say, yeah, but I remember this is the question mark, right? I never say chi-square n minus chi-square 1 is chi-square n minus 1. Okay. Now you may feel this annoying, right? I mean, what's the difference? A plus b equals to c means a equals to c minus b. Well, again, right? That's the difficulty with math. That's an arithmetic statement, right? That's true arithmetically or wherever it is that is true. We are making a probabilistic statement, okay? And you got to be careful. Probabilistic statement may not carry over. Sorry, arithmetic statement, right? May not automatically, right? So a plus b equals to c implies, right? A equals to b minus c, like this, right? But this is equality. This is not about identifying distribution. So applying this here is not direct, right? You don't know if that kind of statement carries over. Actually, that's a mild objection. A more serious objection is this. When you want to use a statement, right? Suppose you want to use the subtraction statement, okay? Subtraction version. There's another requirement that they must be independent, okay? Because of course, if you have non-independent here, then this doesn't work. Well, does this chi-square n and this chi-square 1, are they independent? This chi-square n and this chi-square 1, are they independent? No, it should not be. The reason is here are xi, right? Is xi also in here? Oh, sure. Why not? This is x bar being the average of xi. No, it's fine, right? Again, this is why things are hard. Symbols are hidden behind symbols. So that's why you just cannot play with symbols. You got to see what the symbols are saying. That's perfectly fine. This is a very easy mistake, right? When you see a symbol, try to see behind the scene what it is. Xi is here and Xi is also in here. You don't expect them to be independent, okay? In fact, they're not independent. So again, I'm not trying to say just because Xi are present in both, that means they're independent, because will tell you something different right now. But right, in fact, these guys are not independent. Okay, trust me on that. You just calculate the covariance. They're not independent. So it's not a straightforward conclusion, right? It's not a home run yet. Okay. So one last result that we need is something like this. The first one is a very peculiar result that if you're not used to this, you may be super surprised. That if x1 up to xn are IID, normal mu sigma square, then x bar is independent of S square. Okay? The sample mean and the sample variance are independent under the normal assumption. They're not independent in general, only under the normal assumption. The normal assumption is super special because of that. Now, why is this this case for the normal assumption? This more or less is related to the peculiar result like this. If xy are two random variables with covariance 0, and they have joint normal distribution, you do not know what this is yet, I think, or at least you might not have seen this in a standard course, but I'll just mention this. If somehow they are connected by a normal distribution and the covariance being 0, I think actually you have done the homework in something like this, then they are independent. All right. It's a super strong result in which way? You will always have studied that, your instructor should have emphasized that covariance equal to 0 does not imply independence in general. Okay, I think your homework actually has done a lot of that kind of question in this week. But if you have normal assumption, then actually it's true. Okay. Now, why is this peculiar? The reason is, remember what S square is. S square is sum of xi minus x bar square divided by n minus 1. So I just told you, right, that x bar is here and x bar is also in S square. How could they be independent, right? That's why I say it's strange. The reason is when you subtract away the x bar from xi, somehow that component goes away, blah, blah, blah. I won't explain it, all right? So I admit, right, the intuition I just pointed out, that xi being here and xi being here means they should not be independent, doesn't hold, right, in this case. But it's a peculiar case, all right? But that is true, and that's why you need to pay attention to this result. We will not establish this result, all right, in class. This is something a little bit beyond our course, because you need to drag in the multivariate normal distribution to make sense out of it. But accepting this, all right, we accept this. But if you accept this, then what happens? What happens if you look at the left-hand side here? Then what we're saying is this, right, being n minus 1 S squared. So this right here and this right here are two independent pieces, all right? This right here and this right here in two independent pieces. So you can establish a result like this. Suppose x and y are independent, okay? X plus y is equal to z. Let's say x is chi-square m, z is chi-square n, where m is less than n. Then you can conclude that y then must be chi-square n minus m, which is the result we need. All right. So you understand, right? the independence is still independence on the sum. But what I'm doing is exactly that situation I'm talking about. In other words, right, y here is a question mark. I do not know what y is. I know x, I know z, they're both chi-squares. And then I know the independence between x and y. Then I can prove, right, that somehow y then must have the expected distribution. In other words, the chi-square n minus m. All right. How to show this? Again, right, I'll do some cheating thing here. I'll ask you to do that as a homework question. Again, it's not hard. You use moment chain function, all right? And I'll give you hint and direction. So, but accepting, right, this result, then we got what we want, which is this is chi-square n minus 1 distribution. All right. So a lot of things going on here. And that's because the sample variance, all right, is a complicated object. So I want to stop here in terms of lecture because I want to show you, right, the simulation result to bring home the idea of a sample variance. And we will, again, right, recap the information next lecture and what's important, what's not. But the most important things, as I said before, was the plan that we go through. So the point of the lecture was to establish exactly point 1, 2, 3 here. These 3 points are the central point of the lecture. And the lecture is just to show you rigorously why this is central. And we will use this information again and again, okay, throughout the course. All right, so moving on to showing you the Python code or the simulation. Okay. So here, right, what I do here is I generate, okay, normal distribution, normal sample, okay? I do normal sample with mean 1 and variance 4, okay? And the sample size is 8. This is a small sample size. So in other words, you expect the chi-square distribution to be chi-square 7, all right? So what I do is I go through and I generate 10,000 samples. In other words, right, this is what I say where I keep sampling over and over again, right? I keep generate 10,000 samples of size 8, right? Each sample, each random sample give me a sample variance, right? Each random sample give me a sample variance. So all in all, I have 10,000 values, okay, of the sample variance. From that, I can draw a histogram, and I will have a pretty good idea of how the distribution, right, of the sample variance looks throughout these 10,000 samples. I also will plot, right, the theoretical chi-square density with some degree of freedom, right? This is the density that, we just talked about, okay? And I superimpose, right, the density upon the histogram. So if the result is correct, then the histogram, right, must fit nicely with the density. Notice, right, I do n minus 1 right here, you see, n minus 1, where n is sample size. So let me show you, right, as n changes, let me change n to 5. Right here, right? Don't look at the below. Below is an example to show you that it doesn't work if it's not normal, right? You see n equals to 5, and let me change n equals to 2. So this is 2 degrees of freedom. See, right? The chi-square density changes, but the histogram always fit nicely with it. All right. And then let me do 10 degrees of freedom. Oh, sorry, 9 degrees of freedom. All right. Now, below is a cautionary example to show you that if you do not have normal assumption. So here I do a chi-square, but then, I do a sample variance, but on a uniform population. So you'll see that with a uniform population, the chi-square curve does not fit the histogram of the sample variance. That means that the sample variance does not have chi-square distribution, all right, if you do not sample from normal population. Now, that being said, people still use, of course, sample variance, right, for non-normal population. Otherwise, right, the concept is pretty useless. So sample variance is still used for non-normal population. It's just you cannot say it's chi-square distribution. But then there is an asymptotic result that's very nice, which we won't mention in class so much because it's hard to say it exactly. But the sample variance will be normally distributed if you have sample size large. The hard thing to say is what is the mean and what's the variance of that normal distribution. But the sample variance, right, will approximately have normal distribution. You see here, I draw the normal density. I draw the normal density, okay? Not the chi-square density anymore. I draw the normal density. And I push the sample size to be large, 100. Look at how closely, okay, the sample variance histogram fit with the normal distribution. But this is from a normal population. So you may say, that's not strange. It's actually strange because this is supposed to be a chi-square to begin with, okay? So that means that the chi-square, when degrees of freedom is large, tends to be the normal, which you see in your homework. Finally, right, to show you that this asymptotic result is universal for the uniform distribution, for a uniform population, right? Now I sample from the uniform. I sample from the uniform. It's also normal, okay? But notice the mean and the variance of this one is not the same as the mean and variance of this one, even though they're both sample variance. So when the sample size is large, right, that's why asymptotic result is important. Most of the distribution we talk about will tend to the normal. But of course, in real life, you do not have the chance to sample 100 population, 100 sample, okay, to begin with. And also, right, a lot of times you need exact result. And so this kind of result is important. And that's why we discuss chi-square in our class. Okay, so the code is posted on Canvas for you to see. Sorry for going over time. If you have any questions, I'll be happy to answer. If not, have a good weekend. All right, homework and quiz we post soon. Thank you. Yeah, you too.